Beep, beep. Good, good. Doesn't work. Okay, I think we're good. Okay, this one is nice. Okay, it's working. Cool. Hello, everyone. Hope you're having a fantastic day. This is good. This is good. Yes. Okay, so today what we're going to do, we're going to check out a whole bunch of stuff. I got a nice little study session in the middle of the week prepared for you. We're mostly going to do optimizer coding in a few, and we're also going to check out a few news from ARC-AGI, which is like brand new. It's like from yesterday. Actually, it's from today. No, it's from yesterday, which is pretty interesting. So I wanted to go through this with you folks. Yeah, we're gonna have a bit of fun here. Hi, Hulk Olsian, Chris, how are you doing, buddy? Hey, Pritam. And by the way, folks, don't forget, hi, Vatsa. Don't forget, like, the purpose of this is just to have like a kind of an environment where you can ask any sort of question you want to do. The topic we're going to cover is just like an excuse for you to participate and to ask your questions. Also, we're leveling up. Wait a second here. Okay, cool. We leveled up. We are now officially sponsored, right? So this live stream has found a sponsor, and I found a cool one which I like a lot, which is Scrimba. So big thanks to Scrimba for sponsoring this live stream, and I'm gonna show you a bunch of their stuff because it's pretty good. I've used it a lot. Actually, I was the one that went around and asked them if they could sponsor some of my videos. So I already did a bunch of them with them. And if you don't know, Scrimba is like a platform for learning how to code. It was mostly on the front end type of side before, but now they expanded and now they have a whole bunch of stuff. So you have front end stuff, you have back end stuff, and you have also AI engineering. So if you're interested in AI engineering, you can go and check it out. All the links in the description, but I can maybe show you a bit like what the heck I'm talking about. It's this. So this is the platform, right? And it's really if you want to build like practical skills to learn to code and program, right? So you have a whole bunch of courses. So you have all of these courses, right? And you see like it's mostly front end coded, but since a while they also have all of these AI kind of thing going on. It's not like the deep learning, theoretical content that is there. It's the AI engineering content. So for those that don't know, you have the deep learning stuff where you actually build the models and you learn how to train them and how they work. And then you have like the models that are already pre-trained for you, and then you can use them in various ways. And usually those are LLMs, but it doesn't have to be only LLMs. You can also have like vision models and all this stuff. And then you learn how to glue them together in order to create an application, right? So like deep learning type thing that is more theoretical is to create the model, and AI engineering is to actually use these models in a way that is useful. And this is more on the engineering side than on like the research side, right? So it's a different set of skills. And what I like with this is they're using the same tech that they've been using for their front end stuff, but for the AI engineering. So what I mean by that is if you take, let's say, the full stack developer path, you have like the normal stuff, let's say the HTML, CSS type of thing, but then you can hit the AI engineering courses, and then you have like the fundamental of how it works, right? Because like AI engineering in general is very like, I would say, like front end coded, right? Which means that like you usually hit a bunch of API, and then like they return you something, and then you have this back and forth with an API, which is where the actual model is hosted. And like you stitch them together to do something. So the good thing is that it bring you up to speed with like specific project that you can do, and it shows you like a good overview on how to like actually get you working with the stuff, like it would like an API. And what I like specifically about this, let's say it's like a semantic search. What I like is that you have like the normal stuff with like the videos and all of the stuff, but then after that, like they're usually code that is not in this one. Shit. They're usually code that is provided, right? And you don't have to set up anything on your own, right? Like it's already in the UI. So you see here, there's the video over there, right? There's an overlay, but I can just like start like coding and making a branch right here, right? And then you can start to code the stuff, and then you can start to play with it. You run it on the browsers and everything's fine. You have to get out of there in order to set up your APIs and stuff like that, or like your API skis. But generally you don't have to move. So you can just focus on like this specific content, right? And then after that, if you want, you can just like literally go over there and then download like the whole code as zip. Anyway, long story short, I fucking love this platform. It's great. And now they're sponsoring this live stream. So kudos to them. So that's that. You can check out where the heck did I put this link? Yeah, you can check out like the app over there if you want to, and over here. Yeah, pretty good. They have a lot of free stuff, right? And they have like courses that are more like you have to have a subscription. There's 20% off with this. But start with the free stuff and then like gradually get the pro. Okay, cool. We have a few questions here. How do I enter Kaggle competition from a country that has banned it? Where the heck are you? Like, dude, where are you? Are you in I don't know where it's banned. Like, are you in Iran or something like that? Kurosh, Iloshi, I don't know. You have to tell me more about it. You can use a VPN, but like, I mean, dude, don't get arrested, right? I don't know why would they ban Kaggle? Is it because of it's Google own or something like that? I don't know, man. Like, yeah, but you don't have to do the Kaggle competition if you can't. You can just like do the learning for the learning, and that's that. Or you can like be in a team, right? And have some of your teammates in, I don't know, the US or Canada, and then like you ship your answer to them on whatever you can use that is encrypted. Why would China do that? Like, are you sure? Are you sure it's China? I don't know. Yeah, but that's my tips. And remember, it's not just about like I don't know, winning the competition, especially Kaggle now, right? It's like it's more about you learning the stuff and then like reading other people kind of solution and then try to put them together. That's what's really cool about this platform, is that you get like a bunch of visual on like other people code. You saw my video regarding the no BS guide. Have taken a break. Yes, good. That's good. So for those that don't know, I got absolutely blasted on I got blasted on Hacker News for this. I think it's because of how I wrote it. Yeah, it's this one. For people that don't understand what we're talking about, it's this. So how to stop feeling lost in tech, the Waffle House. So like just to give you some context, I for some reason I started to receive a massive amount of DMs, right? Mostly from college students. I don't know, because it was the end of the summer and then they were freaking out or something like that. So yeah, like I was just trying to help out, and like if I receive enough of the same thing, because I was literally like at the gym writing like 30 pages. I said 30 pages of feedback, and I wrote it 3 times, and I was like I can't just do this. And then I had a few more, and I was like, okay, I'll just write the blog post and then give them that because it's the same thing. that I'm saying every time. And the thing is, a lot of people are feeling lost right now, especially because of AI. And I get it, because you're like, oh, you're not certain about like what's up, what's gonna happen, if you should still like, I don't know, I don't know, do that, right? Do your computer science background, and then like your computer science courses. And so and then they were not sure about what they should learn, if they should learn this tech, this other tech, like PyTorch and whatever. And I told them, like, guys, like, it's not about the tech. It never was about the tech, right? It's about like what you really want. And then you just have to create some time for it, right? So basically the method is very simple. It's like 2 days, right? The one day, the first day that you do is like, you just get out, you just take 2 day break in the middle of the week, right? And then you get out, and then you find some spot that you really like, and then you just go there, and you just try to think about what you really want, right? Like, stop thinking about your course or like your assignment or your final or like your job. Like, stop and think a bit more about like what you want in life, right? In the next 5 years, what you really want. It doesn't have to be clear, right? And then just write your ideas and stuff like that, and then until like it feel good inside, which is like, there's no unique way of living your life, right? So like, just write until you feel good, and you're like, yeah, roughly this is where I want to go. And next day is just like, you go into what I call a Waffle House, right? It's like, I don't know, man. Like it can be a coffee shop. It can be like a breakfast kind of place or whatever. But just go there, right? Like, eat. There's no reason for you to leave. You don't have to go. Let's say you're a library, you have to go eat. You're there to eat, right? Just be there for the whole fucking day, and then just start to do some planning, right? So you refine like the image that you have in your mind about like what you should look like into like a 5-year goal. And then like you try to interpolate, if this is my 5-year goals, like for what I want to be, what should happen in 3 years. And then you do that again in 1 year, like roughly speaking. It doesn't have to be like crisp and precise, but then you have something to work on. And then like you go and then you drill it down, right? And then you do the exercise of not just going through life with like a vague idea, but really trying to drill down into what you want, where you want to go, and then how you're going to get there, right? To the point of like, you have like 100 steps that you think that are one after the other in a directed acyclic graph type of thing, right? From where you're at right now to like your 1 year goal. And then you continue doing this, and then you try to find where like you don't know, you don't have enough knowledge, and then the steps are look too big, right? And then you make a monthly goal instead of a 1 year goal, and then you make like what you're gonna do like in the weekly to get there, and then you're gonna do what you're gonna do tomorrow, because tomorrow is like Friday, and then you have to actually start and then take ownership of your life and stuff like that. And then you get kicked out of the Waffle House. So this is the idea, is like, just start to think about that stuff, right? And as it can be like different type of way you can conceptualize this. This is not a rigid system, but after that, what you end up with is just like, you have let's say like you have a little framework, right? You have a framework, and then you can just like go ahead and then optimize it every day, right? And every week. So, and you should be excited about this. You should not just like feel, oh, I'm gonna have to do this, and then like, if you feel like this is not what you should be doing, right? And like, all the tech ideas and stuff, right, will go inside the little task and the little steps. It will not be a goal. There's no goal of like, hey, I want to learn deep learning in 3 years. To do what, man? Like, this stuff is fun. I love it. But why? Do you want to go into a research lab? Do you want to like publish stuff? Do you want to just get paid a lot of money, right? I try to put that there instead of like the deep learning stuff, right? That's just the rough thought process. Yeah, it's not about the tech, it's about the friends we made along the way. Yeah, so, but I got absolutely blasted on Hacker News about this because I wrote it like yeah, just read it. Cool. I'm gonna sit in a cafe and just think. Yeah, do that, man. Yeah, it's important to have just time for yourself. So speaking of Speaking of stuff, what I wanted to show you, we're gonna do the optimizer stuff in a few. I just wanted to show you something really cool because I don't know, man. Like I read this this Twitter post from ARC, and I found it pretty cool. That like there's two guys that are now in, I don't know, a benchmark, like that is like so heavily disputed, but now their name is on this, right? And they don't have like a massive deep learning research background and stuff like they're just trying stuff out and it's working, and now like they're on there. So I found it like really cool, and we're gonna go through one of the method. But Sensor is saying, if I had an accessible Tim Horton, I would be 1,000 times engineer by now. That double. You don't have to be. It doesn't have to be a Tim Horton. It can be many things. Right? It can be I don't know, man. Like your grandma house, if you feel like it. It can be that too. So what I wanted to show you is this. Look at that, man. Like you see this, right? You see here. There's somebody that's called Peng here, and then Berman in 2025. They were able to get to this level alone, right, with like their code on ARC-AGI, so about 30%. And the same dudes, right, like were able to go up to here, right? And then this is the cost per task, right? So this one is a bit more efficient, but a bit less performance. This one is a bit more efficient, but like, bit more performant, but a bit less efficient. But still, we're in the $10 per task compute here. Like this is like a scale that is growing by like order of magnitude, which is super cool, right? Like they're better technically than like all of this mass of like deep learning mega systems. But like it's not like they're just like doing it themselves and stuff. Like they're automated their work. Like here, this is the human panel where they actually are literally doing the stuff. But this is just like no, I think the humans are more closely here because it costs them nothing to do it. But like here, you have just like two guys that used a bunch of deep learning system and then use them better in order to do better performance at like a lower cost, right? Or like actually no, not a lower cost, but like just better performance. It cost a bit more, but then they were able to wrangle them better than these systems were able to wrangle themselves, which tells me that like there's still stuff to gain, right? So here somebody said, why is Quen 235B so low? I have no clue, man. Yeah, so like why some of them like hit the performance that they're hitting is a mystery for me. It's very cheap though, right? But Grok 4 is really good, right? So like that's fact. Like it's not like I don't know, like a hype or whatever. No, it's actually pretty good, especially for ARC-AGI, right? And these guys, the kicker is they're using Grok 4, which is cool. So we're gonna just go through them. Through their methodology, because their methodology is kind of interesting, and it's not just about like just more tokens and reasoning and whatever. It's actually also about the way they're wrangling these models together. So there's this blog post. I linked it in the description, but I can just like post it here, right? You can take a look at it. So this is the latest one from my guy Jeremy, and yeah, so there is back at the top of the ARC-AGI. So last December I got first place on ARC-AGI V1 with a score of 63.6%. A lot has changed since then. Thinking model had just come out and they were not so good at thinking. One was still in preview. DeepSeek 1 was not out yet. So like the 2025 score that he got was like in the beginning of the year, and then he changed it, right? And then like here in this one he used I think he used Sonnet 2.5. We're gonna just go through like his technique here because it's pretty interesting. So 2 weeks after my score was released, O3 preview bid it handily, getting 75.7. Spending $200 per task, so a lot of money, right? So he was here, right at the top of the thing, but like I think O3 was like wait a second, it was better at him. I don't see it here. But today I got my revenge. My latest program achieved a new high score of 79.6 on ARC-V1 at $8 per task, 25 more efficient than O3, and more importantly, set a new state of the art of 29% on ARC-V2. Okay, yeah. So he's here on ARC-V2, right? Which is much harder than ARC-V1, right? So ARC-V2 is like still at the top, and O3 is like burning cash like there's no tomorrow, and then pretty much not there. Grok 4 is the best of the game, and like they're using Grok 4 to kind of like get this improvement, right? And if you think about it, right, they're using Grok 4 in a way that like is using more compute because like their cost per task is higher, right? So let's just look at the his technique, because it's called they call it like evolutionary test time compute, and it's pretty interesting. So the idea is that there's a genetic algorithm in it, and then he's using the algorithm to generate program, right? So if you read a bit of what François Cholet from ARC-AGI is saying, is that there's like a lot to do with how the LLM works, which is to make functions, right? And then like a good technique to actually solve this puzzle is kind of to do program synthesis, to kind of create a program to solve the puzzle, and then that's the solution, right? Like the output of the program that you generated is the solution to the puzzle. And we know that LLMs are good at this because they can solve Sudoku, let's say, by creating a program to solve Sudoku, right? And then run it. But if they have to solve Sudoku without doing a program, they kind of suck, right? Which makes sense because of they're not like infinite depth, they're fixed depth. So if they have to backtrack in their algorithm, like in their parameter weight, it just doesn't work, right? So that's the idea. So what he's saying is that he's going to use an engine to create like mini program and then to make them evolve, right, with genetic algorithm, which is pretty nice because we don't hear so often about genetic algorithm anymore. But like I think like it's good to revisit stuff from I don't know, man, the cybernetic era, or like the previous different era of deep learning, and then and AI in general, and then try to use them in different ways. So the method, we're gonna see it in a second, but like if you don't know about ARC, right, you have these puzzle and you have like a very limited amount to train with, right? Actually, like here you have 2, and then you have to make an output here. You can make 2 output, and then like if one of them is good, you're gonna get it correct, right? And a human can do this like without any more output or anything, and then they get like pretty high score. So it's easy for a human, but it's hard for a clanker. So like here, let's say you have the input here, and then the output is that, and it's for us it's pretty easy. It's like, yeah, just add a blue dot here. Like I will add it here, 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 and it's done. But for LLM, it's very hard, right? Like they are having trouble because if you think about it, they never saw this before, and they just have 2 like element to play with. Yeah, so that's a bit difficult. So here the solution is this, and there's many ways of doing this. Like last 2 weeks ago, I think we reviewed the HRM, right? And actually, I think it's been a month. And we reviewed the HRM, and then the HRM is basically doing like data augmentation, right? So you can technically take these, augment them, like you like shift them, you like change the colors and stuff like that. You create a whole data set, and then you augment like the input and the output the same way, and then you can kind of train the model to like do that. Just with this, with no pre-training and with data augmentation, you can technically do pretty good. And you can also just not even like need to have, let's say, an algorithm that is learning that much. You can just do compression and decompression, like in compress arc, and get like 35% of the stuff correct. But this is different, right? So this is the method. So basically what he does is that he has like a sequential tree of solution that he's creating, right? And it goes like this. So you have initial generation. The LLM create multiple Python transform function, each attempting to convert input grid to output grid, right? So like in the first attempt that he did, it was purely Python. And then like you have something that is doing fitness evaluation to check if like you're close to what the output should be. And you know this, right? You know this because you have that, right? It's not like you don't know like what you should be doing here. Otherwise, like no human could be doing it. So you have a fitness evaluation to check like how good does the function is at doing the input to output transformation. You have a primary score for like the complete example grid that function solved perfectly. And then like a secondary score for grid that aren't perfectly solved. You can count how many individual cells the function got correct, because like this is a puzzle with like cells, right? So if this is the output, you can like count, okay, these were good, these were not changed. But let's say they put this to yellow for some reason. Well, they have 4 wrong, right? And then you select and you reproduce the best performing function. Like with genetic algorithm, this is kind of how they work. You have multiple generation and you can like vary the amount of generation. And you iterate, right? And then like here, this is the compute they're spending. So effectively, they're taking like the whatever model was good at the time. Let's say it was Sonnet 4. Where is Sonnet? I don't remember. I don't know where Sonnet is. I don't see it anymore. It disappeared. So they use Sonnet in here, and then they use it multiple times in multiple generations. So of course, it will be like not cheaper than Sonnet or Grok 4, right? So you have like this, you're making a bunch of function, you're making 10 of them, you take the top 5, and you like start from the top 5 and then you modify them, right? And then you get top 3 here, and then you do it again, you make 10 of them, and then you get the top 5 again, and then you do 5 of them, and then you do 3 iteration on these, and then you do a top 2, and then you're able to get the solution. And the top 2 is fine because you have to output 2 things. And that's that. So this is the generation that he's doing. And like if you want a visual, this is kind of how it goes, right? So this is the target, right? The function that you need to be able to do in order to solve the puzzle. And then like at first it's look like this. There's a whole bunch of them, right? And then like second generation, they're getting closer, right? And then they're getting closer up to the point where like one of the black, like the X generation is directly in the green. So he's having like he has the right function in order to do the stuff. So anyway, this is cool. And then like it has multiple architecture, one that is using pooling and one that doesn't use pooling. You can check it out. It's a very interesting methodology. But in this methodology, what he was doing, he was creating Python function, right? Now, what he's doing is a bit different, right? So the method that he's using for this is, so this is what he was using before. And now the final architecture use Grok 4, right? And it doesn't use Python anymore. It just uses language. So it uses recipes, right? So instead of having this abstraction of making a Python function, it just have this recipe, and then it's Grok 4 with thinking. So it will have a bunch of tokens that will go, and then it will run. And then it will be able to output like concrete recipe that then can be fed again to the next iteration of Grok and the next context again and again. And then have it modified a bit. So you have the initial generation to generate 30 candidates, and then you have your individual revision phase. So if no perfect solution emerge, take top 5 instruction and run each through individual revision. So it's the same kind of flow, but now it's like language based versus like Python programming based. And at the end of the day, he's able to do the stuff. And the interesting bit is that like, you see me often talk about long context being like the battleground, shit like that. But this is an issue because if you have a reasoning model, it will just spin out a bunch of tokens, and it will quickly fill up the context window that is useful, right? So at some point you can't go further, and you have to do a whole bunch of compression and things like that, because like the context is full, and even before you go out of context, you already used all of your useful context windows. Not all of the context is useful all the time. So then you have like a dead reasoning zone, and then like it doesn't work, right? And you can see the stack trace here of Grok going into random direction. Yeah, so that's pretty cool. Like, do check it out. I really liked the way it was written, and I think it gives you some good idea about like, I don't know, man, like how much we're just not there yet, right? Like there's still so much work to do, in my view, and so much to iterate upon. Like the fact that like you can just take the original Grok model and have like this inference loop kind of running, like inference scaling loop that is running, and then that the more time the model think, and then have this scaffold that just run, and then like structure a bit the information, makes the model just better and have better output for like stuff that are the humans are good at. I think it means that there's something missing, right? And this, I don't know, in my view, like it's close to like, I don't know, the latent reasoning with like inference kind of scaling that can happen in some of the new iteration of the model, like the let's say the hierarchical reasoning model, and there's a whole bunch of them. But I think like that's it. Like I think that's where it's at, right? If you have a good latent reasoning loop going on where the model can just go ahead and then like refine its solution, not in token space, but like just in like the weight space, and then like it has good context to play with, right? And it can like, I don't know, like have a bigger context if need be. I feel like this will already be a massive improvement in what we have. So yeah, super excited here. Yeah, so that's this. Any question here? We have a bunch of questions. I love you to read what I have. You may find use of it. This is a good lesson. I'm glad that you find this is a good lesson. Did they use DSPI? I don't know. I'm not sure. I don't think so. I think they're just like raw. Did it raw with their own structure here. It's more like hypothesis. Yeah, it's more like subset recipe synthesis, like just to give anchor point to the Grok model at the end to be able to actually output the function that is gonna stitch everything together. Yeah, but like it's like a whole scaffolding that you're doing over there. So it's mutation plus crossover for sequential improvement, kind of. Yeah. So in the first iteration, yes, it was. Yeah. So like I think it's a good reminder that it's I don't know, it's important to revisit like the olden days of AI, because there's still some good idea that you can glean from that, and like just like, I don't know, like shifting a bit your perspective and how you are seeing the stuff kind of give you an edge, because then you can be a bit more creative, right? And you can understand these models and how they work a bit more intuitively. So that's that. Any question before we move on to doing a bunch of deep learning optimizer stuff? Hope you're having a good day. We're Wednesday, half of the week is done. We're getting there. Okay, cool. So we're gonna look at this. If people don't know, DeepML is I don't know, man. I love this stuff. Like I love this platform. It's a place where you can like practice like a deep learning, mostly deep learning topic in kind of a lead code way. And I like it because I don't have to, I don't know, like if I want to write something from scratch, I don't have to go ahead and like do the whole framework to test it and to check if it's good or not. I can just like use their framework. So for instance, let's say this Adam optimizer, like I just wrote this whole thing here, and then like I can, I don't know, and I can learn about the topic over here, tell me like what the heck Adam is about. And then when you run the code, you have a bunch of test cases already pre-done for you, right? So you have, let's say, 2 test cases. Sometimes there's not that much, but sometimes like there's like 6, 7 of them. And you can test roughly if like your intuition is correct here and your implementation is good, right? So this is pretty cool. You can check it out. I like this, and we use it sometime to do some from scratch stuff. So let's take a look at a few optimizers. We're gonna go with the easy one today. And we're gonna start. Do we have a momentum? Yeah, we have momentum based optimizer here. So like optimizers, there's a whole lot of them, right? And you have to understand exactly where they sit in the whole kind of architecture, right? So like a lot of people get that the optimizer confused with the backpropagation step. Let me get like a deep neural network. We're gonna draw a bit around. Okay, yeah, this is good. Oops. Copy image. Okay. Okay. No, this is a horrible image. Wow. Okay, perfect. So you have a deep neural network, right? This is a fully connected feed-forward network. And how you start is you have a whole bunch of image, right? Image, like whatever it is, right? Input that goes in here, right? And then like it will fire up in different ways because of like how this thing is wired up. So you have all of this linear transformation. You have like the non-linearity over there, like most likely a ReLU that is gonna go like this. And that's what's going on, right? And then you go like this for the whole thing, and then you generate the output. So this is your Y over there. This is your X, right? And at this point you have what it's called a loss function, right? So the loss will tell you, right, how close you were from your Y hat, which is your prediction, to the actual thing that you should have done, right? And then there's a difference between the two, right? If you did it perfectly because it's a classification problem, you get a good loss, so that it's like very small. If like you were very far, you get a bigger loss, right? Then with this loss, what happened is you're gonna do some backpropagation, right? So you're gonna go ahead and backpropagate the information about how far you were with respect to the loss and what was the each of the parameter involvement in this, right? And you can do that with the chain rule, right? So I'm not gonna go into like this specific step, but basically you're gonna like create like a graph of computation, right? To be able to stitch everything together, and then you're gonna repeatedly use the chain rule, like by going from the front, the end to the back of the model to the front of the model, so back propagation like that, and then you're gonna be able to calculate the gradient. So how much? It's basically like how much like, and we should change the weight here for this model because of this specific class that we have, right? So each of them will go like this, and then whatever the architecture, even if you have a funky one, right, with recurrence and all of this, you can use backpropagation. You can do backpropagation through time. You can do all sorts of things, right? But if you create the computation graph, you can just backpropagate like this. So at this point in time, you're gonna get a bunch of gradient, right? So each of them will have like their own gradient. So each of the parameters in this will have its gradient, and then we're stuck, right? At this point, this is where the optimizer comes in, right? And the optimizer is simple as like, given you have found the gradient, right, for each of these parameters, how should you change the weights in order for the model to get better? That's all there is. There's nothing else. It's just that. That's all that is being done here. So then you can use many of the optimizer. So you take these, where is it? I'll use the gray one. You take these gradient, right? And then you're gonna shove it into the optimizer. And then the optimizer can have many names. It can be like Adam, it can be Adagrad, right? It can be muon, it can be momentum, it can be Nesterov, blah blah blah. It can have like many different permutations. There is so much optimizer they can choose from, right? So these days, what works the best is Adam W, right? Or like a whole family of different Adam. I saw Adam ARC-AGI too for some of the I think it was Kimi K2 model. And sometimes you use like also Nesterov with, let's say, muon over here. Muon also is starting to be more useful. Actually, muon clip if you're using like a bigger model. Yeah, well, that's kind of it. So these two are currently like the big boys, and these other ones that were created are kind of older generation that led to Adam W, Adam, or like even muon. So you use them, and then what will come out of this is like a change, right? So like what will come out of this, the optimizers, is literally a change, and it will answer the question. Answer to the question: how much should you change the weights based on the gradient information, right? That's what it will answer, and then you will do it, and then you're gonna go another round, right? Another round of forward pass, and then you're gonna do the loss calculation, and then you're gonna do your back propagation, and then you're gonna have your gradient, and then you're gonna put it into the optimizer again, and then you're gonna get another change. That's the rough setup that we're dealing with here. Any question before we move on? We have something. I was doing a Google paper yesterday. Faster cascade via speculated eagle actually used a statistical rule from the 1970s. Oh, cool. Yeah. There's a lot of I don't know. There's a lot of new research that is just literally taking stuff from the past and then just reapplying to the new that's it, the reality. We can't do the local. What do you mean you can't do the local? I'm not sure what you mean here. Can. This is a great website. Like, I absolutely love it. You can also DM the guy that made it. It's called Mo. Very responsive. There's also like an open source section where you can submit problem if you want to. So that's kind of the idea. We have a question. Is deep learning used in industry after LLM and RAG? What is happening in real world in industry? Does the classical ML and deep learning being used at all? Oh, well, this is a good question. Actually, I'm going to screenshot it. I'm going to take this and I'm just going to answer it right here. Oh, do you have the link, Mo, to the optimizer collection? I'm just gonna answer this because this is such a good question, right? The question is this: is deep learning used in industry after LM and RAG? What is happening in real world in industry? Does the classical ML and deep learning being used at all? You would not, because for a background, like I work in the manufacturing sector. Actually, I'm a tech dude in the manufacturing sector, and like I kind of, roughly speaking, I kind of help them with their supply chain by using like technology and like a AI system, right? But you will not believe what is going on in the actual real world. It's quite crazy. It's like if you think about just slapping LM and then be done with it, or using the biggest model and then be done with it, using OpenAI and all this. The issue in like established industry, let's say like a manufacturer that makes like, I don't know, like pipes, or like that always worked in the aviation industry and is doing stuff in a specific way. The actual modelization and using AI part is not difficult. Like it's never difficult. Most of the time, random forest, tabular data, we're good to go, right? Sometimes we use LLMs in order to kind of extract the context and then like stitch something together. Sometimes we use OCR in order to kind of be more sure about the structure of like a document that we're structuring and whatever it is. So like the issue is in most of the industry, it's not in the deep learning area or like AI area or like modelization area. It's in the data and then piping it properly. That is absolutely a nightmare. You never saw that ever in your life, right? That level of like, fragmentation of information. Sometimes they don't even sure which information is correct and which one is complete garbage, right? There's a lot of like untangling and getting the context. Also, just getting the context is insane, right? Worked on a project for like 8 months, and it took me like solid 4 months to be able to understand like all of the details that are important for the project that are embedded in the data. And the issue is that in any company that has a big enough size and long history, not all the people will have all the context. So you go into like a treasure hunt of information bit by bit, and you collect it, right? So actually, if you look at at the slice of work, let's say this is a slice of work, right? You're gonna have this. You're gonna have like, what do we do, right? Like literally, a big chunk of it is just like, what the heck are we doing, right? And then another chunk of it is just like where and how the data is structured, right? So here, where the hell is the data, right? Just getting the data is hard. Like sometimes you will gonna have to wait like, I don't know, 6 months to get approval to just see the data. Like it's crazy stuff, because sometimes like in the industry, you may have to deal with like trade secret or like control goods and all this stuff. So you can't just like go ahead and just don't get the information and whatever. Which is when you're a tech company, it's your website, it's your stuff, it's your data now. Like it doesn't matter. In their case, it's like it's not the same, right? And in the company, sometimes not everybody is available to is able to see all the information. So then if you come in and you try to help out, it's hard. And then here it's like, this is what do we do, and here it's like, what can we do? Right? So this is this slice over here, and then it's like, this is actually doing the work, right? Doing the work is here, it's right straight here. It's a little slice, woohoo! Because as soon as you have everything, dude, it's so easy and it's so much value being created. And over there, it's like presenting the work and making sure they understand, right? Actually, this is a bit bigger. It's like this, right? Like that. So I cheated a bit. I'm gonna remove and move that up like that. Stretch it like this, right? So this is like doing the work, and then this is like explaining the work, right? Explaining. That's it. That's how it looked like, right? That's it's reality of it. So if you're interested in doing deep learning in the industry, it's just not the right spot, man. Like it's not about that. It's about helping people, right? So if you go and you really like an industry and whatnot, use deep learning as like a tool, right? Because like sometimes none of this is possible if you don't have a deep learning or a machine learning model or LLM or like a RAG system that you're stitching together. But it's not about that, right? It's about their problem, right? And to be honest, really, really honest here, right? Most of the time, a good old visualization will do the trick. Like, I'm not even joking. Like, just them being able to visualize their data, you slap it in front of like the person that has the most context, and my man, the problem is solved most of the time, right? Other time, it's a bit more complex and you have to do some processing and whatever it is. But most of the time, it's just this. It's just like being able to visualize their data, because it's such in a bad state that like there's just no way for them to do anything with it. Yeah, XGBoost, man. XGBoost, keep it in your back pocket. The tabular data, like for sure, like it's mostly tabular stuff. And then you can do it this way. After working Caterpillar, I can understand how tricky it can get. Came out of the hellhole of the data, which only for... Oh, this dude was in the trenches. Oh, like it. Cool, nice, man. Working at Caterpillar, this is insane. I work with a few aerospace company. I also work with Grib. They're in the construction space. Anyway, like I work at a few of the company in the space that he's mentioning. But how tricky it can get came out of the hell of the data, which only 4 people understand, working in the world with good understanding of ML and DL. Cool, man. This is good. And to be honest, like it can be hell, but remember, it's hell for everybody. It's not just you, right? It's like imagine if like, I don't know, man, there are 7 database all out of syncs, right? Nothing working really. And then people are kind of just having all of these different systems on the side, and the stuff need to go, right? In the not tech industry, you don't have the same way of working, right? You can't just duplicate your stuff that is creating value and then work on it over here. If you're in a production line, like literally it never stops. If ever it stops, your business is messed up. Like you're losing money, right? And like they're not operating on a hard margin. So what happened is that anything that you're doing, you need to be doing while the stuff is continuously spinning out, right? You can't stop the line to do a little test. We're gonna like A/B test this stuff. No, man, it either work or doesn't work. And if it doesn't work, you might get blacklisted for ever touching this line ever again. And like when I say line, it's not just the production line. It's what happened before with the data and after, right? Like all of the process can be affecting everything else. So it's very sensitive. And a lot of emotion also, because like if you're messing something for other people and then other people get shit for, and like it can get very political very fast. So you have to be very careful, right? So I hope I didn't discourage anybody. Yeah, it's not a walk in the park. You have to love. If you love the industry that you're in and you're working in, it's a bit easier. Hi Yassine, will you be okay with having a study session on RNN, LSTM, and sequential networks sometime? Yes, I would. I tried to code the backpropagation one time, and I completely failed because I got stuck for like 45 minutes on an element. But yeah, for sure, I should go back into the sequential network sometime. We have another question. It's a dumb question, but can't we use evolution algorithm itself to improve the LMW or any other optimizer? There's many ways you can do it, but like remember, like LMW is not like it's this all stuff is not cheap, right? So you're gonna improve what over here with the evolution algorithm, like which element of it, right? And how are you gonna test it? So that's kind of the issue, right? And then like if you test it in a small network, it may be not the right parameters that you're gonna use for the big network. So you have to do a whole parameter sweep in order to figure out what's up, right? What people tend to do, right, with these optimizer, is they tend to kind of create a bigger abstraction over it, right? So QH-Atom is an example of something that did that, but it's not used at all in the industry. Shampoo actually, I should do a video on that, is, if I remember correctly, a superset over Atom, right? W. So like it's bigger than Atom. So if like it should be strictly better than Atom if the right parameters are tweaked. But it's usually about the parameter that you're choosing. So like one cool thing is that if you want to like right now, what the field is doing is that it's shifting toward using benchmarks, right? But also for optimizer. So this like how's it called? It's called GPT speedrun kind of competition, right? Where you are trying to make an optimizer that will like a nano GPT speedrun that will train nano GPT on the cipher, right? And try to be as cost efficient whilst being like as performant as possible. And right now, the one model, the one optimizer that is the best is Muon. But you have to understand, like all of these have very high like biases about like their construction, right? Like if you think about it, AdamW, the two biases that it has is that it's about the momentum and it's about like additive gradient, right? Two ideas that came from Adagrad and then momentum. So it's combining those two together. There's hyperparameter to play with them, right? So it's kind of like a superset of momentum and Adagrad, right? That is pushed together. Actually, not Adagrad, but RMS prop, which is an improvement on Adagrad. So it's slamming them two together. Muon is kind of the same idea but it's specific for specific layers, right? Nesterov is like you have momentum, but you have momentum with a look ahead just to check out if you're good. But it's all biases that people put in there, right? That kind of do have some grounding in reality, but in truth, like is that we don't really know 100% like what's the best that we should put. So everybody was picking up optimizers, but to be honest, most of the time AdamW is the one that you should go for, right? And then also, even if you take Muon, you should have also AdamW because Muon just work on specific layer. Yeah, so this is the situation that we have right now. Any other question? Those are great questions, guys. Keep it up. Yeah, and I hope I didn't discourage anybody from going into the industry. Okay, so let's take a look at the momentum optimizer. The momentum optimizer is like, I would say, like the iteration on stochastic gradient with momentum. Stochastic gradient ascent. That is like was the most useful back in the days, and then like the idea of momentum stayed in various forms. Like he went into Nesterov, right? He went into Adam W. He went still into muon, right? So all the idea of having a momentum of in the when like the gradient, like the loss is descending in the cost plane is good, right? So it's a good idea to have that. So the basic idea is that we can take a look at it here. You have a parameter that will take into consideration what is happening in the past, right? So it doesn't move like stochastic gradient descent. So stochastic gradient descent move like this, right? It move like this, that you start somewhere, and then it will move in like direction like this, and then it will change direction afterward, right? In each step, it will move like that, right? While momentum will go like this. If there was a momentum to go, I don't know, like in this direction, based on the previous gradient, it will kind of keep it, even though like it's pushing, like the update step is pushing it here. It still has this overall momentum to go a certain direction. So if, let's say, the other step is course correcting it into another direction, it will still kind of move in the overall direction. But you see now it's kind of using it like using more of this, and then it will go a bit like this. So it's a bit smoother, right? And it can go over bump in the loss plane that is just a local optima. And this is good, because otherwise the model will kind of get stuck into local optima and it will never converge into like the best solution. So yeah, this is the momentum in a nutshell. And you have like you have basically two element here. Actually, we can check this out here like that. Whoops. Woohoo. Okay. Right. So this is the whole algorithm. Like the optimizer algorithm are never complicated. I've never seen one that was more than like, I don't know, like 25 lines of code. Right. Most of them is like even smaller than that. And this one is like 2 lines, right? So you have like you have a bunch of parameter. You have a velocity term here, right? Which is like the element that is aggregating the information, right, from like the past time step. So you have this. Sorry, you have this that is over here, right, from the previous time step. You have a momentum parameter here, which is telling how much of the past should you take into consideration going forward, right? In this case, it's this one, right? So it's over here. So you're doing this multiplied by that, and usually it's in the 0.9 range, right? In Adam, it's actually, I think it's no, it's still 0.9. So it's usually 0.9, right? But this is tunable. You can decide. If you put it to 0, you don't have momentum anymore, right? You see, like this momentum thing is like of a superset of stochastic gradient descent. It's like stochastic gradient descent is momentum, stochastic gradient descent with momentum, but with momentum set to 0, right? It's the idea. N is the learning rate here, so it's like how big of a step you should take, right? And remember also, for the learning rate stuff, usually you have a scheduler, right? You don't use the same learning rate as you progress through the model training, right? So this also goes into consideration. I'm not gonna cover this, but just know that the learning rate usually change a bit. And then here, this is actually your gradient, right? So this is the gradient over there. So basically what we're saying is that we're gonna take a bunch of what happened in the past, right? And we're gonna add it to what's happening right now, right? And this is gonna be our velocity that we're gonna apply to, like, so this is our velocity here. And we're gonna apply it to the parameter. So this is how we're gonna do the update. And then we're done, right? Remember here, you like, do not get confused. Like momentum is, optimizers are so much easier to understand when you get that part, right? So the gradient part is not in the scope. It's in the previous scope for the backpropagation. So if you take into consideration that you already have your gradient, right? Because the gradient calculation is like optimizer agnostic. It doesn't matter, right? So you already have your gradient. Then you can use like and just see like these 2 lines and be done, right? So this is momentum. There's really nothing else to that. Any question over here? Yo, I just realized that there was already like a collection. Look this, look at this. There was already a collection for optimizer. So a corrected set of problem. Can I just go through them in sequence? I'm not sure. It's like, yeah, it would be nice if the collection was like in sequence of complexity. I would love that. Yeah. Okay, so this is that. And that's it. So if you were to code this, it's not that difficult. Like if you think about it, right? So what do we need? We need to, we have already all of these parameters, like all of them are given, right? And then we just need to multiply them properly, and then we're done. Like there's nothing to it. And if you look here, we have these parameters. I'm gonna actually gonna take that so we can read it, right? So what do you have here? We have our parameters. So this is our theta over here, right? It's over here. We have our gradient. We have the velocity, which is the parameter. No, this is the previous velocity, right? So velocity at this is like the v at t minus 1. So this is v at t minus 1, right? This is our learning rate. This is good. This is our new. And this is our momentum. So this is our this parameter. I never remember what it's called. So this one, and then you just like are gonna return the updated parameter and the updated velocity, and you have to like return the velocity that is new now, because it will be used and be shoved in the next iteration over here, right? So this is the situation that we have. So let's actually code this, and so let's go with if I remember correctly, we're gonna have our new updated velocity. Actually, I'm gonna zoom in. Sorry, guys. Okay, do you see? Yeah, you can see. Perfect. Updated velocity equal. We have the previous velocity, right? Time the momentum plus, and then you have your learning rate times your gradient, right? This is your velocity, and then the new parameter, so updated parameter equal, you have the parameter minus, is it a minus or a plus? I think it's a minus. Yeah, it's minus. Minus updated velocity. Cool, and then we return these. We're gonna return that, and then we're gonna return this. And if we run this, should be good to go. I don't think. Ooh, first try! Wow! Yeah. Okay, this is it. We got it. All right. Easy, not even hard, right? So there's nothing to it, right? This is something that I posted yesterday on Twitter. That like, how to say it? Like, the deep learning is like machine learning and deep learning. It's not about the code, man. Like, there's nothing in the code. Like, look at this. Like, if I was to show you this and say like, hey, this is stochastic gradient descent with momentum. Like, there's nothing in it that is inherently informational at all, right? Like, there's no information that you're gonna glean from it, from the code. The reasoning behind why things are is not here. It's somewhere else, right? It's in the little drawing that I did to you, right? Because I like this is better for the model to kind of go around and the cosplaying. That's kind of why like it's done like that, right? And that's kind of all there is, right? So like if you're having trouble with like knowing how you should train yourself to do deep learning and whatever it is, don't try to just like jump into the code and then just look at the code, always be in the code. Try to take a step back and try to understand like the context and then the ideas behind the algorithm, because some of the ideas is just like we thought it was a good idea and it worked, right? That's the reasoning, right? I think the original transform architecture was like this, like it worked, guys, and it's good, right? That's it. This is all I have for you. So a lot of it is just like that, like why did they do it this way versus this way, and then why this work and this doesn't work. So there's a lot of confusion and like blurriness because it's very empirical. People are just trying stuff out, and then sometimes it works, sometimes it works like dramatically well, and sometimes it doesn't work, right? So yeah, that's kind of the gist of it. And you can continue, and then you can test out a few of these. It's good to go and then actually code it to have a check mark, because like, okay, now I can understand like why each of the bits are there, or have an intuition about why this is important, and then you're good to go. We have a question. Representing the model learned for the backpropagation can be wrong inside, but the output of the model is correct. That also is the problem happening in backpropagation. Yeah, it doesn't matter. Like as long as like with, I don't say it like deep learning is really about the output, right? It's just about like, it doesn't matter how it does it. Like you can literally not really see unless try to do like mechanistic interpretability of like all the model and whatever it is. But like, it's just about the output. Is the output correct, right? Are we doing good here? And is it like reliable within the bound that I'm interested in? And if the answer is yes, even if it's doing it in like the most messed up way you ever saw, right? Literally doesn't matter, right? So sometimes this is a problem, because you're gonna end up with some solution that are correct within your distribution, but if it just go outside the distribution, the messed up way that is doing the solution will not apply. But for a human, it will be like, yeah, of course, you don't do it like this, you do it like this, and then you can do that and that. But he never saw that, so he never know, right? And sometimes it has to do with how internally it is learning, or it is structured. And a good example of this is like the previous model, they didn't have a residual stream that they were learning, right? They were trying to change all the parameters at the same time, right? Kind of, right? To get to the output, which is super hard to do. And then you're capped, because as you get more parameter depth, very hard to move all of these layers together. So one change that like was introduced that was super useful was to add a residual kind of a connection, which changed what the model was trying to learn. Now it's just trying to learn in each layer enough, and then you shove the residual to the next layer, and the next layer will kind of work with the residual that it has, and it goes like this. So if in the middle you're already done, and then all the depth in the middle is not useful, you don't have to do anything. You can just like let them pass the residual. That's what they do, and then you get the output. So learning residual is easier than to learn like all the parameters at the same time. A small change that has big implication, right? But like it's very difficult that the reasoning why this was like it was a bit vague, but they actually work, and we still have this, right? And I think this is the way to go. I think it's the way to like, I don't know, like figure out intelligence is like, I don't think you can go at it necessarily. Like you can get a lot of information from first principle and from like the neuroscience and all of this, but at the end of the day, it's like, does it work, right? And like if it works, but now, oh, it doesn't work for this, like, okay, let's make it work for this. And then you go and then you iterate. And by iterating, we're going to hit like all of the different issues, and then we're going to get better solution. But just like we did with reasoning, right? Like reasoning was a simple change. It's like just spew out more tokens and then use that as scaffolding to be able to do a better output. That's all there is, right? And it worked super well, right? Now, like there's test time, and then like we're doing like we're wasting a lot of compute here. It's not necessarily optimized in any shape or form, but you get better answers, right? Isn't that the wrong way to learn? I don't know, man. Like, it depends. Like, what's the right way? Like, same for when you teach your kids, and like you can see it in babies actually. Like when a baby will try to learn how to crawl, they will do it in the most fucked up way you've ever saw. Like some will just not, they will just, depending on the floor surface, some will just like slide, right? like they swim and whatever it is. Some they will crawl because that's kind of what worked for them, right? And after that, they kind of iterate. At some point, they're tired of like hurting their knees, so like they start to stand up in a more like normal way. But I think it's all about like what is useful for them in this environment, and like what is the point of it, right? You don't get mad at a baby because he's just crawling like in a weird way. Can he go to point A to point B? The baby is happy, right? It doesn't matter. He can get to the gagagoo at the end, right? So like for him, it's like, yeah, got it. Now I can move on and do other stuff. It doesn't matter how he actually did it. For you, you can be like, oh no, it shouldn't do it this way, but it doesn't matter at the end of like, can you move? Yes, okay, it's good. So it was a weird tangent. Cool. That's actually any other question, folks? That was good. Thank you, gamer, for participating. Okay, we got this one, right? Let's take a look at a few other ones. I'm gonna do it like a caveman mode. I'm gonna write here optimizer, and I'm gonna get these, and I'm gonna do them one by one. Okay, so Adamax is an old one. Adamax and Ala Delta are two old one. Let's actually do momentum, Nesterov, because Nesterov is tightly related to momentum, right? And it's a weird one, right? Like the gist of it, right? The gist of Nesterov is you're doing momentum, right? And like if you were to be a ball rolling down the plane, like, and you had eyes and you were seeing what's going on, and you see that like, I don't know, man, like this direction you're going is messed up and it's gonna go like this or stuff like that, right? Or maybe it's gonna be a good idea to shift a bit before you get there in order to continue the momentum in the area that has the most usefulness. That's the idea. It's like you look ahead, you kind of cheat, and you're like, I'm not stupid. I can see a bit further down, and I'm gonna go there instead of there. I'm just gonna adjust a bit my trajectory. So that's the idea of it, and yeah, it's just a funny idea, and it works. It works good. And in Muon, this actually is inside Muon. So you have Nesterov inside, and Nesterov work better than just the plain momentum that there is in the Muon algorithm. So that's that. Let's actually look at what's up. It's usually, there's different ways of implementing it for the look ahead, and it all has to do, there's all bunch of trade-off that you can do with it. But let's take a look at the parameter that we have. And by the way, this is one thing that I like with this. Yo guys, honestly, like use Crimba for all the AI engineering portion, and then like if you want to learn the theory in a way that like is like engaging and like you actually touch the keyboard, use DeepML, because there's all the learning section here. Pretty good, man. Like you get all the information in a succinct way, and then like it's done. So here we're actually gonna get the key difference over there. Okay, cool. So let's take a look at the parameters, and you're gonna see everything will click, right? So there's a look ahead that you're doing before, like that you compute before, and then that you're gonna apply, right? And there's multiple ways that you can do that, right? It's basically a linear interpolation about where you're gonna go. So you take your previous parameter, right? And then you apply momentum now, right? So you're doing the momentum type of thing here, right? Without the gradient stuff, just like with right now. And then you kind of try to figure out where you're gonna be if you're not adding the gradient that is right now, right? And then with this, you have your new parameter space, right? Where are you gonna be, right? And then what you do is you're gonna have the gradient calculated on that, right? So that's what the gradient is calculated here. Usually this is not how it's implemented. It's not how you're not gonna calculate the gradient, but like after, it doesn't make any sense to do that like that. Like I can show you a bit. Muon algorithm. Where is it? Where is the code? PyTorch implementation, and then we go into Muon, And then we have our torch. Yep, here, look. Here. This is the mu1 update, right? And if Nesterov is true, this is what you're gonna do, right? You're gonna do your momentum, right? And then with the grad and the 1 minus beta, whatever. Like it's the parameter that you're using to get like to do the momentum. And then like if Nesterov was true, then what you're gonna do it again, right? You're gonna do a linear interpolation again, but this time you take your momentum that was previously there and then you interpolate it with beta. So there's no gradient recalculation that is happening, right? So like this is super important. There's different ways of implementing these algorithms that kind of just depends on like what you need. So if you're confused sometimes that something has the same name but not the same implementation, like sometimes the guys just wanted to go fast, right? And then they tested it and it didn't make a dent. It didn't make a difference whether they were doing this or actually doing the recomputation. And then there was a paper that was published that was like, hey, yo, we tested a whole bunch of stuff. They are the same. Cool. Now they can use it. But if you learned it like this, and now you see this, you're like, what are we talking about, right? Where are we not calculating the gradient again, right? Anyway, the end of the rant. So you get the gradient here in various different ways, or an approximation of it, right? And then this is what you use with the learning rate, and then you reuse this again. So it's like you're doing momentum on where you're gonna be, and then like you adjust, right? And this adjustment is what you're gonna use here. And you see it's a bit wonky here. You're just not gonna apply the like here. No, it's good. It's the same, sorry. No, it's good. So you're gonna apply the parameter update here with your new velocity, and then you're good to go, right? The key difference from classical momentum is that the gradient is evaluated at look ahead, t minus 1 instead of t minus 1. So that's kind of all there is. Any question, right? So basically, you go down the plane in a momentum, let's say fashion here, but like when you're here, you're gonna look where you're gonna land technically here, right? And you're saying, hell no, I wanna go faster. And then you go like this, right? That's kind of the idea. W stream, yes, we're doing good. Tout semble, I'm gonna talk in French, folks. Tout semble facile lorsque tu parles. Je suis confus, tu sais en ce moment dans ma tête. Imagine une feuille blanche et il y a des informations un peu partout. Ah, okay. We're gonna take a break, guys. I'm gonna do some therapy with you here. Over there. I'm gonna translate this for you. Should maybe do a stream in French for like the 3 people. So what we're saying here is that everything is easy when I talk about it, right? People are confused here because there's a lot of information, right? Like, to be honest, folks, there's just so much in deep learning. Like you can go an infinite amount of depth, an infinite amount of rabbit holes, right? You don't have to know everything, and you shouldn't, and you can't, right? So that's okay, right? It's fine to not like get all of the information all the time, because I think it was Noam, the legendary guy at Google now that came back, that was attention all you need, good researcher, and what he was saying is that all of us were working on the transformer architecture, but none of us really understand it fully, right? We just know it works for our purpose, right? That's it. And then like there was optimization that was done from the transformer like ad nauseum, like they changed the positional encoding that was happening in sinusoidal form to the rope form, and then all of the different change happened there, and now it's better, right? They didn't get it right the first time. And one thing you have to understand is like you're in a domain where it's very empirical. Like there's a lot of like, yeah, we vibed, we had the vibe check idea here, and then like it actually worked, so we went with that. And when people are starting to ask you why it worked, you can backpedal and try to find reasoning about why it worked. But to be honest, like most of the time, it's just like we tried this and it works. And then after that, other researcher will look at it and like, it was good, but actually if you do it like this, it's better and it's fine, right? So you have that deeply embedded in it. Like there is no objective like truth or form, right? It's very difficult to find some in why stuff are working the way they are. So it can be very overwhelming. So take it a step by step, right? Like sometimes I read stuff, I'm like last stream I tried to explain rope, I butchered it because like I wasn't able to explain fully. Now I have to do another video and another stream and then take good information and explain like where it come from and what's lineage. And it's totally fine to not get everything all the time, right? Like the best thing that you could do though is like you take like something you want to do and you try to get there, right? And then you get as much information as you can in order to advance this project versus just trying to learn for the sake of learning, right? Okay, and then we have another question. Tu peux parler un peu sur les transformations que l'on fait? Exemple, les dimensions des tensors, move to GPU or CPU. Oh, that's a good question. Like how we like do the change and transformation, and how we go from to different like tensor shapes, and then we go from the GPU to CPU. These are two different things, right? There's how you move around with the matrices and how you shape them together, and then how you actually take information and optimize it to like go from either like put it on the CPU or load the GPU, or how to make your stuff run better on the GPU generally. So two very different aspects. There's a good book for that. Like I think it's this one, Deep Learning with PyTorch. Yeah, this one. Is it? Yeah, this one is free. Is it free or did I find a stolen version? No, I think it's free. Okay, yeah, cool. This check this out, right? So, Faima, check this, right? So this is the Deep Learning with PyTorch book. Over there, right? And like, if you're having trouble conceptualizing the tensor, how they're moving, and honestly, like sometimes it's just so complicated because there's so much and they're so high dimensional, but also how they work with, let's say, PyTorch, because usually you're gonna do all of your stuff with PyTorch. You're not gonna do it yourself, right? I greatly recommend this book because it was made by some of the maintainer of PyTorch, so they know the internal of how things work, right? And like it's a really good book because it introduced the PyTorch library in like high level, but then the second chapter is like the tensor and how they work, and there's really good like visuals over it. So they show you like all the different like dimensionality of the tensors, and then they tell you like with example with the PyTorch code like how it works, right? And then they tell you also like how in the memory it is set up. So if you're doing stuff with like GPU or like or CPU between the two, like there's ways of doing your stuff that will be more optimized because of how PyTorch is actually representing the tensors. So yeah, so this is a very good book. You don't have to read all of it, but there's massive information in all front. And by the way, there's one of the guy is a neuroscientist. So you actually will have an exercise over here that I love. It's like volumetric data, like with brain. And honestly, like you rarely get to play. Like usually people in complexity will stop at like images, but like volumetric data, fMRI, is another world because there's a 3D like voxel that we call, and this has meaning, right? And then this is in a grid, right? And then like you have to analyze this in like a 3D space. I find that when you add another layer, like another dimension to the data set, it helps you conceptualize how you should move stuff much better in the lower dimension, let's say on images and stuff, because then it's like flatter, or like in text, which is a bit like one-dimensional. Yeah, so check it out, Faima. Don't have to read the whole book. I would say like read it from chapter 1 to the end of chapter 3, and then here you see moving tensor to GPU. It will answer your question. and it's gonna be useful. And then you can practice a bit more, like with project over there. Really good book all around, and you can just steal it from for free. The book is all there. Oh, this is for you guys. Any other question? We're good. Okay. So we're over here. So again, so this is not too complicated. We have to double check what they're giving us over there. Here. Right there. Oh wait, we just got another good question. We're gonna make like a very small step in the Nesterov, in the optimizer in general. So somebody is saying, how to convert tech knowledge into business, interview, question on case study, converting POC to actual revenue, and working on justifiable KPI to ROI. I love your question, Kartik. Like, they're very practically focused. I don't know if like you're a consultant now or something like that, but like, it's super good. So like, this is the question, right? How to convert the tech knowledge to business, like literal money. We're talking here, right? Interview question on case study, converting POC to actual revenue, and working on justify KPI to justify your work. So how do we make money with this? So this is gonna become like an Alex Hormozi live stream. Yeah. So anyway, like, how do you make money with this? So, like, technology. Like, I know this because, like, I long story short, like, I built the startup, and now we're doing like not so bad, and we have clients and stuff like that. And I did a whole bunch of consulting, and I work in a few companies. Like, the way to use tech in order to like make money is to actually help people. This is the secret sauce, right? This is insane, guys. I'm gonna tell you some, like, if you help somebody and like the help they need is high value enough and they can justify why they need this help, right? To remove some pain that they have in whatever shape or form, you can ask them money and they're gonna give it to you. And I'm not even joking. Like, this is not just some like this is not just some like a sarcastic type of answer. Literally, like, this is all there is. So, and the important bit is you have to figure, because like most of the time people, especially in the industry, they don't know like how to say it, like how to solve their problem. So sometimes they will say like, I need help with AI, right? Or like, I need help with this problem, and they don't know the solution is like an AI system, or like the solution is like a CRUD application, or just changing how their database is set up or something like that, right? They don't know. Most of the people, like, get out of Twitter. Most of people, they have no clue what's going on, right? Absolutely no clue. So like, the best way to like make a living with like technology and like and all this and like AI is being very good at listening to people problem, and then like trying to help them out, walk through a solution, and being able like also to focus on solution that has high value for them, right? Because it's useless to go and say, I'm gonna do AI for you, you need AI and AI, and then you go in and do it, and they lose a bunch of money, and then like, why are we doing this stuff, man? What's going on, right? And then they're not happy, and then it's done. So you have to be good at the tech in order to see where it's useful, right? And then you have to be good at listening to other people's problem, right? And then to give them a solution, right? What the flow I usually like to do is I go in there, I listen to their problem for like an extended period of time, right? A business problem, not like a tech problem, a business problem. And then I try to shape iteratively like the leanest solution. Sometimes I include AI, sometimes it doesn't, that solve their problem. And then I walk them through why it working, and I get more context, more feedback, and then we get something that looks really good. And if you're educating them at the same time, they trust you. And if you're already looking like you know your stuff, they already trust you, and then they're gonna hire you, and then you can do that. And you see here, I never ever mentioned build an application. Never mentioned that. It's helping people. Sometimes you help people at scale with an application, but it never starts with the application. It starts with actually helping people. So once you do that enough, and then you have some feedback, okay, I helped this guy like this, help this dude like that. Is there other people like him? I really like this. And then you do it, and then, yes, there's 7 people like that. Oh, is there more? And can I do less work because I'm doing a lot of stuff, like I'm doing a lot of the same thing. And then you realize that like I can build an app and then like do it like this. And then you can get more clients, right? And more people are happy and they refer you to their friend. And at some point you're like, hey guys, instead of like always coming back to me, would you prefer to have this application? And people are like, yes, we want to have this application. We love this. And then like they tell their friend, and then like then you have a business, right? That's kind of how it works. So that's the flow, but it all starts with helping people and listening to their problem. What are we talking about right now, Yassine? Good question. We're talking about money. No, we're talking about optimizer. Just somebody had a practical question. Hey, little brother, new here. Love your content. Cool, man. Keep it up. We're here. We're doing optimizer stuff and educating the youth. You realize how clueless people are about AI when you're at the family gathering and you have to explain your job. Yes. And like, do you know why they're clueless? Because it most of the time doesn't matter for them, right? It literally doesn't matter for them. So it's up to you, right, to figure out how you can help them out, and then maybe include AI in the mix or not, right? Most people, like, they kind of have this feeling that there's a solution, but it's very vague, and then like it's up in the sky. So being able to untangle them is like seriously one of the best business skills that you can ever have, because people are willing to like throw a lot of money at you if you're able to find a solution, if it includes AI or not, right? But like what is happening with AI is that some lingering business problem, right, in most of these companies are now solvable. Before it was not, right? Now it's solvable. So because of this, if you're able to find it, there is so much pain in there. They were gonna pay you whatever you need, right? And then they're gonna be able to justify this to their board or like their CEO by saying like, I remember this that cost us $1 million. We can solve it for just like 600K, right, or something like that. And then he's like, what? Go, green light. Let's go. Let's do it, right? And then it doesn't exactly work like this, but like it's the gist of it. Totally agree with that. Be useful for people and you're good. Yeah. And then you get a referral, which is fantastic. Okay. What do we have here? We have our parameter. So this is fine. We have a gradient function. Oh, we have a function as a parameter, right? This is like functional programming type stuff. And then you have velocity, and you have the learning rate, and then you have the momentum. So the gradient function here is like, you know, it's not like that. There's not the gradient function in your deep neural network, right? It's like an approximation that you can have, and it will look like this most of the time. It's like this is your gradient function, right? It's like a linear interpolation type of stuff. So the theory is telling us that we should like go back and do the back propagation again, right? No way, man. Like there's gonna be so much waste to do the back prop all the time, right? For a temporary parameter to do a look ahead. So it's an approximation actually that we're gonna do. By the way, like this, you see this all the time. Like this stuff where you have like the theory, right? We should be doing this, but actually, like you're doing like an approximation of it is everywhere. And if you start by looking at the approximation, you might be lost about like what the heck is going on. Oh wait, somebody wanted the book name. It's Deep Learning with PyTorch. Deep Learning with PyTorch. We're giving some tips for everybody. Yeah, so a good example of this, I'm gonna show you. This one. Muon is a good example of this, right? Because like this is the algorithm for Muon, right? It's just this. It's like you compute the gradient, then you're doing the momentum or Nesterov, and then you do this weird thing, and then you update the parameter. And this weird thing is kind of just like singular value decomposition, but it's Newton-Schulz, right? So if you don't know that you're trying to do singular value decomposition and only take the U and the VT, right? What you're gonna end up with is you're gonna look at like the actual curve they're doing, and then you're like, what is going on? What in the hell are we looking at right now, right? What is this? What are we doing here, right? This squiggly line is Newton-Schulz. Where did they find that, right? Like, and then it become hard because like, okay, you have these parameters that look a bit random, they look like this, and then you backtrack and you're like, what are they trying to do? And you realize they're trying to approximate a sine function, and then you're like, how is this a sine function, right? For not initiated, the sine function is like a very dumb, simple function that look like this, right? It literally look straight up like that. This is a sine function, right? You see, it has -1 here for all the x's, and then it go poof straight to 1, right? Technically, it goes like this, right? But like not at 0. That 0 is like undefined, right? But technically, it goes like this here, right? And then you look at this and you're like, how? How did they come up with this? And why did they come up with that if they're trying to approximate a sine function? And then you read more about it, and then you understand like all of the little elements. But if you just saw this, you might be like, yeah, I'm too stupid for this stuff and it's too complicated. But in actuality, what's happening is a very common pattern where like you have that, this is the algorithm, literally, there's nothing else. This is it. But like this is like 6 steps that they're not telling you, right? From the get-go, they don't have to. And the step is that we're actually doing a stochastic gradient ascent here. We're doing, singular value decomposition here, right? And then we're throwing away the singular value. We keep only U and V transpose, right? That's what we do, right? We can't do that with SVD, too costly, right? So we're at step 4, right? So we're gonna use approximation, right? And the approximation that they decide to use is one with like how is it called, odd polynomial, right? Polynomial. If you apply it multiple times, you can get U times VT, right? If the function is a sine, is roughly a sine, right? And then like they don't need to get exactly a sine. They just need it to look like a sine in the bound of the data. And then they figure out that like actually there is some jitter. It can be above and below 1 by roughly 0.3. And that's where you got this absolutely messed up Newton-Schulz, like a squiggly line. It's an approximation of a sine function that has a buffer of 0.3 above and below the 1 line. But like this is it. Like if you want, you could do just this, right? Just singular value decomposition, throw away the singular value, and you're good to go. But it doesn't, like no one will use it. It's not useful. So everything you're doing here is approximation to still have something useful with like the core idea that you have, but that is actually usable by users. And this is the same thing that is happening here, right? This is not theoretically what's going on. It's like a function that you can use in order to kind of interpolate what's happening. And you can just use a linear interpolation here and you're good to go. Okay, perfect. So let's do it step by step. So first step is we're gonna take our parameters and then we're gonna find a look ahead by doing minus the momentum that we have times the previous velocity. Okay, so here we have parameter look ahead equal the parameter minus momentum times velocity, right? Now we have that, and then we're gonna calculate the gradient, and then we're gonna do grad function, and then we're gonna give the parameter. Perfect. No, sorry. Look ahead. Okay, so now we're here, right? We have that. We can then do, what is it? It's the velocity. So the updated velocity equal our previous velocity times our momentum. I prefer like this. Actually, I'm gonna put it bigger for you guys. Right, and I'm just gonna put myself super small. Like that. And then it's a, is it minus? No, it's a plus. Plus the learning rate time our gradient, right? So this is like, I'll call it look ahead gradient. Why is it fucked? Okay. Gradient. Jesus. Okay, we got it. So this is our updated velocity, and then we just like update the parameters. So then we go updated parameter equal our parameter minus the updated velocity, and we're good to go. So this gonna go here, and this gonna go here. Is this it? I think it's good. So let's check it out. Nothing worked. Name parameter doesn't exist. Okay, yeah, I messed up. Parameter. Okay, name parameter. It will be easier if we knew how to write, right? Okay, it's good. Getting there. Okay, we got him all right. Perfect. Good. That's it. It's these 4 lines of code, right? Pretty simple. So now we have Nesrov, accelerated gradient. So basically, for recap, you kind of look ahead in this kind of future state that you're going to be in. You calculate the gradient in this future step, right? And then you are able to do the added velocity on that versus on the actual parameter that you are right now, on your actual gradient of the parameter that you are right now. Okay, cool. Any question? It's pretty simple. It's not that bad, this one. Okay. We can go to another one. Then we have Adam, we have Ada Delta, we have mu1, Ada Max. Which one you want? Which one you want, guys? That can I do? I can do all of them. So if you had to vote, which one are you interested in? Are you interested in Adagrad? We can take a look at Adam over there. Ada Delta, which is like a very old algorithm here. We also have mu1, if you want to take a look at it. I already have a full stream on mu1, so it's not too bad. We can actually take a look at that. So if you have a preferred algorithm, do let me know. But other than that, I think I can go and take a look at, you want to do mu1? We can do mu1. Like it's not that complicated, right? So actually I can go through the algorithm for you. Full. Wait, did we do? If we do momentum, then you can understand mu1 directly because it just use mu1, right? So I can show you the different steps. So this is what we have, right? Right here, right? Over there. And actually this is good because mu1 can use both momentum or Nesterov can use both of them. So this is mu1, we have that, and then we have the update step, the Newton-Scholz approximation over there. And sorry. Okay. So there's a whole bunch of stuff that are very familiar to you now, right? What you have your parameters here, you know them. You have your current gradient, you know them. You have momentum buffer, right? Which is the same thing as before. There's nothing different. It's the velocity that we were talking about before, right? There's a different way it's calculating it, which is closer to Adam, which is an exponential kind of moving average, right? But it's kind of similar. It's the same idea. Then there's the momentum factor. We saw that. There's the learning rate, right? And then there's the precondition update. Oh, well, this is different, right? This is the only thing that is different. So the precondition update is like what's happened when you shove whatever you have as momentum into the Newton-Schulz algorithm. This, when you pop it out, this is what's happening here, and you're doing like your parameter update on that. Actually, here, well, actually, I already have it. Where is it? Here. Right? So all of this is the same stuff, right? So this, we already know how to do that. The computed gradient is already pre-computed for us. This part, we're already good to go, right? With the momentum, because it's the same thing we've been doing. Like just the thing that we've just coded right now, momentum is this. You can replace that with Nesterov if you want to, but you just have to do the two-step within. And then here, this is where it's new and it's scary. It's the Newton-Schulz setup. So then we can go into that. Well, you'll see it's not that bad. Once you get that out, right? You see you're jamming the B, which is the buffer, momentum buffer here, and something new pops out of it, right? And something new is what you applied the learning rate on to update your parameter. Before that, we have a question. Hey Yassine, I'm struggling to pick a niche. Everything from AI to research to neuroscience feel interesting, and I end up reading a bit of everything. How do you figure out your own niche? Oh, this is good, man. This is so good. That was me, man. Like I did a whole bunch of stuff. Yeah, man. Like yeah. The actual answer to this, right? To like how do you pick your niche? Like at some point you're gonna have to make a decision if you want to actually have an impact, right? If you don't want an impact and you just want to explore stuff and like whatever, you can just continue what you are doing and then you're good. At some point you gotta eat. You might want to have a family. You want to maybe have some goals in life and whatnot. Yeah, maybe your mom is on your back to get a job. Like all of these are gonna play into consideration. So, but like, how do you figure out like the niche that you're actually gonna work in for extended period of time? It all boils down to your goals in life, not in the tech, not in neuroscience, not in like any of this, but like in life, what you want to do, right? And based on that, this is where you can like orient a bit your learning and then like go at it through it. Actually, I think you missed it. Where is it? This blog post over here, which boils down to this again. We're circling back. So it's the same thing, right? You're gonna have to like find a bit your let's say it like your why. Why are you doing this? Like where are you going? Like why you find neuroscience so interesting? Why you find AI so interesting? Is there something you want to do? Right? Do you want to actually do like research and publish paper, or like are you more interested in getting a job at different places? Are you more interested in making discoveries, right? And like helping other, like this, all of this, you have to figure out for yourself, right? And then once you figure it out and you're like, I want to be this person, roughly, then you can detail how this person, what this person accomplished, right? And then you have to be a bit pragmatic, right? Like you're not going to be a Kung Fu master, 20 times Olympian, super linguist, and then like have a Nobel Prize, right? Like most likely not, right? So you have to be kind of pragmatic and go back down to earth, because you're gonna have to try to figure out how you're gonna actually do it. And the the best chance to do something is just to do like a few things for an extended period of time. However, right, one thing I want to add here is that like the goals are nice and all, but there's something a bit deeper that you can find too, right? And for me, that one thing that I found when I was younger was that I really like to learn, but not in the sense that it is a goal or something like that. A bit like you right now, right? It's like a thread in my life that I really like that. Like I really like the process of learning, right? Not in the I like to learn to cook or like I like to learn to skate. Though I like the process of learning to cook. I like the process of learning to skate, and thinking about that is joyful to me, right? It's kind of the stuff that I realized, and I like that, and I'm good at this, right? So what I did is I actually, if you look at what I've done in life in that lens, everything makes sense. Studying neuroscience, why? Because this is how I get a better idea about how learning is done, right? And then like studying machine learning and AI, I like learning, right? So if we can make a clanker learn, then I get a better idea about like what learning is about, right? And sorry for the slur word here. I'm gonna stop saying that. Like if you're able to make an AI learn, like you get a better sense about like how you learn and how can I apply this to myself, and then just like getting this knowledge in my head was so good, and then you can use it in various different ways to help people out by teaching, right? Like and this thread hasn't dampened down, and it can't, because it's something that is outside of how to say it, like of any sort of goals, right? But I also have pragmatic goals, because I know that if I'm just alone and depressed, but I'm still learning, I'm not going to be fulfilled in any sense, right? So I'm trying to make sure that I can do and follow this thread of life, which is learning, in something that actually makes the life works, right? And this is why I went to entrepreneurship also, right? Because entrepreneurship is just like learning cranked to the maximum, right? You have to learn, otherwise it doesn't work. You can't just know everything from the get-go. Like you need to learn about finance, you need to learn about HR, you need to learn about the process, you need to learn about problem from your user. There's a problem here, how do you solve? Like all of this is always constant. But for me, it's good because every day I get to like follow this thread some more and learn a bit more about that thing. For some people, there may be other thread. Maybe a thread for you is like spirituality, right? Maybe a thread for you is like beauty, and you want to make like beautiful stuff. Yeah, that's kind of it. But you have to kind of like, the answer is not with me here, Aniket. The answer is like with you. And deep down, you have to kind of take a step back and try to figure out what you want in life, like deeply and also like pragmatically. So we're going into spirituality right now. This is good for the optimizers. Okay, so we're back here. Great question, folks. Keep it up. Okay, so Newton-Schulz, right? The idea of Newton-Schulz is that, actually the idea of muon is like, there is some issue with Adam W in general, right? And the issue is that if you look at the gradient update step, right? Some direction are disproportionately bigger than others. So it means that, like, let's say you only had, I don't know, man, you only had like three axis plane like this, right? Like the thing is moving in mostly one direction, and then the update step in the other direction are super tiny, right? They're just super, super quiet. And what the people are saying here is a vague feeling that like, maybe it's gonna be better and more stable if like all direction was the same, right? Like all direction, we can inject a bias that like all direction are good, and we should have all direction being equally important. So this way, these little itsy bitsy tiny direction steps are actually gonna be like more loud, and these gigantic direction step will be actually smaller. And then we're actually going to go into the direction that makes more sense, but it will be roughly now a ball that is rolling the cost plane, and not this messed up thing. Like a good analogy that I had is that I don't even know if it's a good analogy or not, but like analogy that I had was LMW is like at some point, right, trying to roll a boat down the cost plane. Like it has a specific shape, and like it won't go in one direction. Like you're gonna go into most likely another direction. Versus what muon is trying to do is take that boat and slamming it back into a roughly round shape so that it can roll down the cost plane a bit more evenly in all of the possible axes. That's the rough idea. And like the inner idea is that this is a good thing, right? That's the bias that they put. And when you test it out, actually, like muon is actually pretty solid, right? There's ways you have to do a bunch of stuff, but like there's definitely some usefulness. So Aniket said, thanks man, that was really helpful, but the way I was really impressed when I saw that you research consciousness, you're also great at ML and you solve supply chain problems. But it's all the same for me, right? To be honest, it's all the same. It's all about that little thread that I'm following, and it's super fun, man. Like I love it. Okay, cool. So let's dive right here. Hey, Omnimorphic, glad to have you on the stream. We're finishing up muon. So how we do it? How do we do that, right? How do we do like this kind of ball crunching thing, right? So the way to do it is actually there's a way. It's like it's the singular value decomposition. If you do a singular value decomposition, right, you're able to get like another plane that is orthogonal, which this also is good, right? But also to squash out the singular value. So the singular value actually, if I look at it here, I'm gonna put out some archive here. Jesus. Here, right? That diagram. So the singular value that you have here, right? You go from this, and then you're gonna do a rotation, and then you're gonna get like a stretching happening, and then another rotation, and this resulting thing with this this form here, right, over there, Jesus, we got it. This form, right, is like something that is orthogonal now, right? So like the singular value that you have here have a meaning, and they have a profound meaning about like the shape of the matrix. And then these U and T and V is how you make the stuff kind of more separate to each other with less overlap, right? This is the magnitude. So if you want to actually squash that boat into a ball, the only thing you have to do is like set this magnitude to 1, right? If you set it to 1, then you just get the orthogonalization, but you don't get like the stretching. And that's the core idea. Like if you do that, then at every update step you're doing this motion, you're gonna squash the ball. If it starts to grow in a direction, you squash it back to like a ball shape, and then you can roll. That's a rough idea of it. And you can use singular value decomposition directly, but it's not fun because it's gonna be like super slow. I can't understand what velocity expressed. It's like you have to understand it a bit. Like I know it's a bad analogy, but like a ball that is rolling down the cost plane, right? And the gradient is telling you where to roll, right? To go lower, so that the loss will be lower, right? But the issue is that if you don't have velocity, you're always gonna move like in a very saccadic fashion, right? So if the direction, overall direction, this cost plane, the geometry of it tell you that you should go there, and you're just like, you're gonna get stuck at some point in like a hole like this, even though like it was deeper like that. So if you had no velocity, right, you would do this. You would be like, oh, I need to go down. Oh, I can go down. Oh, I'm gonna go down. Oh, I'm down. Oh, I can't move here. I'm stuck. If you had some velocity, you'll be doing this. You'll be like, wee-hee, and then you're gonna be down here. roughly speaking, right? That's what the velocity expressed. This is in 2D, 3D is same thing. And as you go more dimensional, like it's very hard to see, but the idea is that it's still a fundamental truth in these higher dimensional space. And like with the topology of the Cots plane, you can kind of prove that a bit. That's roughly what the velocity express. Okay, cool. So like the idea here is that if you wanted to like kill this one, to like make it disappear, either you can manually set it to 1 after doing the singular value decomposition, but it's garbage. You don't want to do that. You want to find another way of doing it so that like it's automatically set to 1 while you're calculating the singular value, so that you have your u and your v while you're doing this, right? And the way to do that is if you shove the singular value into a function that will like kill the singular value with a sine function, you should be good. So the question is like, which function you can press on M to do this on the sigma, right? The singular value. That's roughly the idea. And can this process be faster than doing the singular value and then manually replacing all of the singular value, doing the singular value decomposition and then replacing all the singular value by 1? Is there a process that is faster? It turns out that yes, there is. Okay, Gamer, I'm just gonna finish this and then I'm gonna answer your question. So what works is Newton-Scholz, which is a process where you take an odd matrix polynomial and it has a specific property. If you apply a function that is odd, like that has an odd shape like that, right? What happened is that if you apply it to the M, it will just, it's as if it will apply just to the singular value, exactly what we want, right? So now, theoretically, if we can make like this function look like a sine, should be good. We can't use a sine because a sine is not an odd matrix polynomial. It's just not a polynomial at all, right? Like it's this function, right? This is not odd and this is not a polynomial at all. So it's a piecewise function. So what we need to do then is just to find an approximation. And what happened is that if you have an odd matrix polynomial and you apply an odd matrix polynomial on the odd matrix polynomial, you still have odd matrix polynomial. So you can kind of recreate the sine function by stitching together a whole bunch of odd matrix. That's the idea, right? And then they tried, there's a whole bunch of ways to do it, but the Newton-Scholz way, it works super well. So you can do a cubic iteration here, which is you apply this function 5 times to the input. So if you apply it 5 times, at first you have this. Does this look like a sine to you? No, a sine is like this, sine is like that, and like that, right? This is not what we want, right? And also, we don't want the full sine. We don't need this part. We just need this part, right? Because we are trying to set the singular value to 1. So this is not good, but if you apply it like 5 times, you get this, which is not bad, right? It looked like a sine function up to like approximately here, 1 point something, right? Actually square root of 3. But after that, it's all messed up. After that, it goes down like this. So if your data that comes in to get squished back is kind of in this range, it's still good. Like it will be just fine. And so like you start to put the idea in your head that you're gonna have to kind of normalize your momentum buffer that comes in into a shape that fit this range. Otherwise, it will not work. You're not gonna be able to do this approximation. So you can also do a quintic iteration, which is this. So you have x, x3, x5, right? Before it was a cubic, which is x and x3, right? You can use a billionth if you want to, right? It's just that the more you use like iteration, the more compute you're gonna use. So at some point there's no reason to use muon or to even use an approximation like this because it will be slower than singular value decomposition. You apply this 5 times and you get this, right? Which is a bit cleaner, right? Cleaner than before, right? But it's still within the bound. The same thing here, you can try to do like 6 different iteration or 5 different iteration with different parameter, and you can get like something super clean here. It's just great, right? What the folks figure out is that there's 2 requirements, basically, right? That when you give the buffer, it goes to 1, right? In this function, and that, so you have to kind of normalize, and it is within the bound, right? So you have to normalize it to make it fit in the bound. So this is the idea. However, like the guys, when they were running this, it's actually Keller Jordan, when he was running this, he found that like you don't really have to have one exactly. It can be 1.3 and 0.7, right? It's fine if it is within this range. It doesn't have any impact, right? So empirically, again, right, they tested a whole bunch of stuff and then like it worked, right? So then they were like, yeah, within this bound it worked. Higher than that, it doesn't work. Lower than that, it doesn't work. So we have this range to play around. They also saw that like 5-step to do like the iteration on the polynomial, don't need 10 step, just 5 is good. And sometimes you can even go to 3, right? So that's that. So this is what they found. And then this is where they get what we call the cursed quintic, right? So the cursed quintic is absolutely disgusting, like from a purely aesthetic perspective, because it looked like this, right? It looked like a whole bunch of squiggly line, and then we kind of lose the idea of a sine function. It's just like, it needs to be kind of a sine function, kind of in this region here, right? It can't be bigger than that. It has to be within this and that, right? That's what they found, and then they optimize it, and then this is the parameter. So this is your A parameter, this is your B parameter, and this is your C parameter that you have, right? So that being said, here's the Newton-Schultz algorithm, right? And it just looked like that. So you have your A, B, C that I just discussed, right? And then you have the normalization step that I just discussed. And then like there's a whole bunch of stuff that they're doing here just to make sure that it has the right shape to do the algorithm. So if like the thing is too long, it will do it like this, do a bunch of like orthogonalization, and then shove it back like that. That's what we have. And here, right, it has to have 2 dimension. Like it cannot have 4 or whatever it is, because mu1 was specifically designed for a specific kind of like a weight matrix. It's only for the dense weight, then for the dense linear layers. So it doesn't work on, let's say, the embeddings, and it doesn't work on the biases terms, right? So it only is for these dense 2D matrices. And that's that. And then here, right, this weird A, B, X thing, like if you were to like actually unroll it, right, you will see that at the end of the day, you're going to get A times X, and then you're going to get plus the B here times X, which is B is like times A, but A here is X squared. So you have B times X squared, X3 plus C times X4 plus 1, so X5. So this is where you're going to recoup that, and there's just like a more optimized way to calculate it. That's it. That's all there is, right? So this is just trying to approximate this with the specific parameter that we discussed. Yeah. Okay. So you can also actually watch the other stream or like the full video that I done on the Muon clip to understand it. And if you look at the actual implementation, they're doing momentum, and then they're doing Nesterov, right? And then if it's like a convolution filter, they split, like they shove it back into 2D form because they need to. And after that, they do like the Newton-Schultz here. And at the end, there's this stuff that is happening divided by, wait a second, the update that they just did times this. This is what we call how's it, like a prefactor, right? And it's needed for in the derivation of mu1 to kind of stabilize the stuff. But like it doesn't look like exactly what they said. It's a different version, so people are still playing around with this. But the prefactor is kind of used over there. What the Jeremy Bernstein told me is that it's a way to think about this is directly is that we want weight matrix to send input vector with L2 norm of square root of fan in to output vector with L2 norm of square root of fan out. So we need a conversion factor. So this is the conversion vector, right? And it's like giving a specific bias in what this shape should be before to scale the Newton-Schultz output. This part, if it was complicated, you can check out Jeremy Bernstein thing. He tried to kind of condense like 6 years worth of research into a blog post. Yeah, that's the idea. And one thing with mu1 that is cool is this. See that? So this is Adam. This is another. It's mu p. and this is like the full dualization. So this is like you can think about it as mu1. So usually when you train on like small network, right? Specific learning rate are good, but when you train on bigger network, it's a different learning rate that is better, right? To get the lower loss, which is an issue, because then it means that you have to do like, you can do your experiment on a small network, but when you're going to go into the big network, you're going to have to do a few test run to check out like what the learning rate should be, right? And you have to kind of approximate it. A lot of compute wasted. With mu1, what happened is that, look at this. The actual good learning rate for the small model and then the bigger model, order of magnitude bigger, is kind of the same. Like even if you took literally the same one, right? You could hit in the bigger model not so bad performance. So there's what we call width transfer with this dualization setup, which is pretty cool, right? There's also like other property that I'm not gonna go into, but like yeah, that's the rough idea for mu1. Okay, cool. We have a few questions. How important is the neuroscience in AI now because of the DLM, because they're not the same anymore? To be honest, like how important is the neuroscience? I think it's still pretty important. Like I absolutely love when I see a brain in an AI paper, like with the hierarchical reasoning model, even if it's like semi-related, because then I think there's still a lot of stuff to like grasp from how the brain is working, and different type of brain, right? So with the HRM, what is interesting is that they're looking at a specific region in the hippocampus, right, of the rat, which are good at like solving puzzles, technically, right? And then they've looked at like different region that talk together at different frequency. One that is looking more at the input, the other one that is like looking more at the like a grander scale, and then just like aggregating the information. So yeah, this is cool. So like, and these ideas are refreshing because then it like spun out some other stuff that you can use. So I think it's still very important, but like it's never directly important because their substrate is so different. Like you cannot reproduce exactly what's happening in the brain in silica, and because like if you think about it, like what's happening in the brain is a billion mini CPUs technically, right, that have their own little weight. They're all running in parallel. They're not like running one at a time sequentially. Like it's all living things that are running in parallel. So if you're trying to reproduce this in silica with like sequential, it's a bit weird, right? It's a bit weirder. So it's not a one-to-one. It's never one-to-one. But you can glimpse some information that is kind of a universal, and then try to apply that to the model. One thing I like right now is like the reasoning, latent reasoning model. Also the CTM, the continuous thought machine, right, from Sakana. I think these are good ideas. I think like doing the thing in the latent space and then trying to like be a bit more brain-like with the HRM. I think it's good. I think like honestly, I think they were into something with the hierarchical reasoning, even though like it was debunked. Well, not debunked, but like it's not as important as we thought it was for the ARC-AGI. I still think that like there are a few tweaks away to having something that is good. I think like having multiple layer of reasoning embedded, and then having like this kind of latent reasoning loop where like the data is being processed multiple times at different like scales of resolution. I think that's a pretty good idea to do. Yeah. So hey Yassine, I started reading through the mu1 paper and there was this quote: an old idea in optimization theory said that since the gradient is a dual vector, it may not be subtracted from the weight without learning rate and applied to the weight. Can you explain how it is a dual vector? To be honest, not in a good way. I will not be able to explain it in a very good way. I might, like, what I could do is like maybe I could read it a bit and then stop a bit and then structure my thought a bit more in that, and then I'll be able to give you an answer. Cool, man. Okay, perfect. Thank you. Good. So let's actually clear this up, and then we can maybe call this a day. and I can go walk you through the actual code. So there's two motion here, right? There's the motion with like Newton-Schulz, and then the rest, right? And the rest, if you look at it, if you look at the code, is dumb simple. There's nothing to it, right? And you could do it right now easily. So your step one is you compute your buffer, right? You see here the parameter we have our parameter theta, we have the gradient, we have the previous buffer, right? And then you have our mu, which is like the velocity factor, right? And then you have the learning rate. So what we have here is like we're calculating a buffer, and then we are shoving it into Newton-Schulz. Don't think about it, right? And then you use that thing that you shoved to calculate your data. Done, right? You can compartmentalize this in your head, right? And now only think about the preconditioning with Newton-Schulz. That's it. You don't think about the rest, the momentum and all this stuff. Oh, we have a new supporter. Thank you, James. Thank you. Really kind of you. You don't have to do it, but thank you for supporting the channel. Then the Newton-Schulz is exactly what we saw. Like remember when we saw like the whole algorithm? I don't have to show it. Like the whole algorithm with like the A, B, and C. It's the same thing, right? So there's nothing to it. You have the A, B, and C here. Then you have the normalization, and then you can use multiple normalization that you want here. The Frobenius norm is good enough. Like it's the most basic type of norm. What you're trying to do is you take your X, right? So you're actually your buffer, and then you try to jam it between 0 and square root of 3. If you do it here, you should be good to go. If you let it raw like that and you comment this out, it will be too big for the approximation and it will be complete garbage, right? So you keep it like this. So you shrink it, and then you're calculating here your odd matrix polynomial, the quintic flavor, right? Using this parameter, which is the Kerr's quintic, so the one that which is a bit squiggly. And then you're doing this 5 times. So this is the steps, right? So you're doing it 5 times. So you do it once, twice, thrice, fourth, and 5th time. And this will give you like the little squiggly. If you just do it once, it will not be that, right? Remember, it will actually look, it will look more like this, right? Just a line like that, which is not good. This is not what we want. It's not a sine function, right? It doesn't make any sense. So this is good. And then you return, and then you're done, right? This is your S or your O, however you want to do it. It's your precondition output. And that's that. There's nothing much to it on muon. If you want more details on exactly how muon work, I did a whole much better edited video on this. And actually, I also have the muon clip. So muon clip is the version that is used in Kimi K2, right? And basically what they saw is that muon was a bit unstable on like a specific like a attention squirt. So the logit exploded. So they have to clip it also every time to train like in very large model language model. So with the trillion parameter, muon is still good. But remember, this is only for the 2D dense matrix. It's not for like all of them. So you still have to use Adam W in some areas, but in general, it leads to a much better training algorithm. So the dualization math felt pretty straightforward, but I just couldn't intuitively understand why it needed to be done. You know what? I'm actually going to read it right now and try to come up with a good explanation later on in the day. So that's it, folks. I hope this was useful, right? I hope this was good. We have another question. When to use which optimizer in real-world use case for sparse and dense embedding? When we'll encounter which one? Most cases, use Adam W, straight up, right? To be honest, even if you're training, like, let's be real, guys. Like, none of you will most likely train ever a large language model to a size of 1 trillion parameters. Like, it's just not happening, right? It costs millions of dollars. And compute. There's just no way, right? What will happen is you might like either fine-tune the model, RL it, right? And in these cases, it's not about the optimizer that much, right? There's none of it in there, right? In this case, you just use ADAMW and you should be good to go. The way to kind of think about it is that you should always look at the literature, what they're doing, and just do that again, right? Just do it. Don't try to use like very different things. Even if you're trying a small model, try to use what the literature is saying is the most stable, and start there. Spend more time optimizing the parameter of the best optimizer versus trying to come up with your own that is different, right? Until somebody else have like optimized something and then bench like a stress tested that it's good. Like what the guys at Moonshot did for Kimi K2 is absolutely insane if you think about it. They did a trillion run on an optimizer, right? That was before only trained in like 1.5 billion parameter model. And now they scaled it to a trillion parameter model. Actually, they did it at 15 billion before. But it's insane. Like the amount of money they spent in there was crazy. But it was justified because of the performance gain they got in the compute and the cost budget, and also in the literal performance. But like it's not up to you to do it. It's more like these labs. And if you're in a lab and you're doing that, then it's different. So yeah, generally, dude, just use ADAMW and you're good to go. An optimizer can also just be an input parameter. Try it in a tuner. If you have an infinite amount of money, yeah, do that. And infinite amount of time also, because at some point time also is one of the parameters that you in your cost function, right? Like you can wait 10 years for your grid search over all possible kind of optimizer ever. This is good. Or yeah, you do like a genetic algorithm on the optimizer. How is it possible that Muon research was done in 5+ years? Wow, like but like the Muon folks are absolutely insane. Like it's a bunch of people that are working on like dualization, all this. It's like highly connected to shampoo, to like MuP, and then like it's one guy, Keller Jordan, and his team that like he just tried to maximize this benchmark with the best optimizer. Like they throw at it like super fine-tuned ADAMW and try to beat it with Muon or other kind, right? And then they figured out that Muon was actually good. So the research on this I also improved, because like the folk that Moonshot saw that this was useful. They trained like a very small model at the same time as DeepSeek R1. So it was published in the same day or something like that. So nobody read the paper actually, but Muon worked, right? At bigger model size. And then like they did it again with Kimi K2, and now we have like a very good model that is behaving a bit differently than the other ones, which is interesting. But even then they had to normalize it properly. So yeah, that's it, folks. I hope this was useful. It was really fun. We did a bunch of momentum based optimizer. We can maybe do some of the other one afterward. You had a great question. I want to thank the sponsors again. Thank you, Scrimba, for sponsoring the stream. And if you have to learn like really practical skill to build app, check their stuff out. It's in the description. And if you want to test the stuff with like a lead code style problem, go check out DeepML. Awesome application. And I wish you all a fantastic rest of the week. See you guys.